So it's great to be here. I've always wanted to visit NIMBioS, and this is my first visit. And I flew in last night, so I couldn't see anything from the plane, but I believe it's a beautiful area. I'll have to come back, I guess. I'd like to thank Fred for inviting me to various workshops where every time I've got to give a talk, I think, now, what should I talk about? And I really had to scratch my head for this one because I wasn't quite sure how to frame it. And this is something I've been concerned with for quite a long time, is teaching systems thinking in applied sciences. And this whole business about modeling and having models out there that people can use versus building your own models is something that I've been very interested in. And so I'm going to try and explore this topic. But as I went into it, it didn't quite work in the way that I thought it was going to work. But I'm coming at it a little laterally, and I hope it does work to some extent for all of us. So let's get started. I found this on the web, and I thought this is absolutely perfect for my talk. And that is, the greatest enemy of knowledge is not ignorance, it is the illusion of knowledge. And there's nothing better to give yourself an illusion of knowledge than a highly detailed computational model of a complex system, especially one that you can't really test very readily to see whether it works or not. So for example, these models that predict storms, and there's a European model and a US model now predicting the path of the latest storm. And in a week, we'll know who was right and who was wrong. But if you're looking at climate change models, something that's going to say what's going to happen in the next 30 years, 50 years, kind of Club of Rome type stuff, maybe 50 years later, you can look back and say, what a silly model, or what a lot of nonsense. And so we had the illusion of knowledge at the time. I also found this very interesting book online, which was put together by the National Research Council Committee, Frontiers at the Interface of Computing and Biology. Is anybody in this room who was involved in this? And published by the National Academies Press. So this is now a decade old. And they have a lot of different sections, and this section is computational modeling and simulation as enablers for biological discovery. And they talk about statistical analysis and discovery of large-scale patterns. And this, of course, is coming more and more true. And Leslie's talk was a great backdrop for this. For exploring this data-rich environment, simulations and computer-driven models of biological systems are proving to be essential. So let's talk a little bit more about this. This is, notice the simulation and computer-driven models. And here we have to make a big distinction between big data and data mining and the process of computational models and trying to understand processes. So in this NRC text, why build models of systems? There are 12 points, and it's exactly what you would expect. Provides a coherent framework, highlights basic concepts, uncovers new phenomena, identify key factors, link across scales, formalize intuitive understanding, screen hypotheses, inform experimental design, predictive values that cannot be easily measured, link what is known to what is yet known, generate accurate predictions, and expand range of questions. So this is all kind of boilerplate stuff, why we should build models, why we should teach students to build models. This is not really what my talk is about. My talk is about the following, what I call a conundrum. So this is the first thing I'm going to say, and then the conundrum is going to come up. The utility of software applied to big data problems, such as identifying patterns, classifying or categorizing objects tagged by data, is self-evidenced through the results produced. Either something useful emerges or the software fails to produce good results. And you'd say we have a weak method or a strong method. A weak method, you'd go in, you'd look at data, you might not detect anything. A stronger method may do better than this. But then the second part is the validity of software used to evaluate the impacts of management actions on complex ecosystems is very hard to verify prior to such actions being implemented. So we've got models, we build them because we want to use them to manage, and it's hard to verify that these models are actually any good, but we're compelled to use them because we have nothing better. And once implemented, actual outcomes can be compared to predicted outcomes. So, you know, like the hurricanes coming through, we can see how well we did. But this is often a one-point comparison with experiments hard to repeat, and time horizons are generally large, sometimes multi-generational. So here we can say we have good versus bad models rather than weak versus strong methods, but we don't know well ahead of time which are the good models, which are the bad models for many of the things that we try to do. And that's why we're so bad at sort of macroeconomics. We always get it wrong because there are major things we've neglected, like individual politicians. Who could have predicted that Donald Trump would be so popular? And what happens if he becomes president? We have no idea what he's going to do to the economy. He may be fabulous. I don't know. Do you want to risk it? So there's a lot of software out there that's being developed for all sorts of things, and they're powerful tools. So here's an example of a platform that could work very well without the user knowing the physics. So you work in the drug industry, and you might want to know about the functional properties of a particular protein. You might want to see how it folds and its functional units, what they look like. You run the software on your protein amino acid sequence and you get something. Do you have to know the physics of protein folding to effectively use this? And the answer is no. These are very robust physical principles. The people who designed these actually knew what they were doing. And by and large, over time, we can tell whether the software really works or not. And you've got a new novel sequence of amino acids, you might want to see what it's doing. You can put it in, and you don't need to know the physics to have some confidence and for this particular software to be useful. So here's an example of a platform that provides a knowledgeable user with a very useful tool. So these very often software that helps us visualize stuff. We understand our system, maybe we don't understand our system, but we've got a lot of information. It may be stuff on networks, and we can get this information. Maybe it's from Twitter, or maybe it's from something else. And we want to try and understand this better. And this comes from organizing the data and visualizing it and using our brain, which is the most marvelous pattern recognition machine that we know currently. Although, we can't go through things as rapidly as a modern computer. We can certainly do better for each individual picture than any modern computer. And so you can have lots of data, and you can use software to help you find your way through, and it's very useful. This brings us to the kind of software that I'm really talking about. And here's an example of a platform that may be very useful, but could be dangerous in the hands of an unqualified user. So I don't know, has anybody here used Ecopaths with Ecosome? Yeah. So fortunately, Lou knows something about the processes he's modeling, so he's a qualified user. But then there are a lot of folks out there, they may be in government departments, they may have a bachelor's degree, they may even have a master's degree, and they may want to do this stuff, but they don't even have much ecology. And they've got this tool on how to put elements of an ecosystem together and to build a model. And this is where Hawkins' dictum is possibly true, that you can build something and you might have the illusion of knowing what your system's going to do and actually believe that you effectively know what your system's going to do, yet when you run your model, you get all sorts of output, and you're now going to use this to make management decisions. So I want to talk about preparing applied scientists to use models as an aid to manage complex environmental systems and ecological systems. And I'm going to talk about two examples that I've been involved in and sort of show you the kinds of models we've developed. And these models actually can be used by people who have no knowledge of really how the system works. And in places where I might be very reluctant to use the model myself in order to make management decisions, other people may be quite happy to take these models and use them. So the first example is an effort that I've been involved in for many, many years. That kind of ground to a halt 2 years ago. We have the model, but we haven't really implemented yet because the department's actually run out of money after spending a lot of money on this. So this is the California Department of Fish and Wildlife, and they are charged with recommending dam release schedules on various river systems, in particular here the San Joaquin River system, to protect and conserve fall-run Chinook salmon. So they have a mandate to do this. And the other example I'm going to talk about is related to the outbreak of Ebola. And of course, WHO, World Health Organization, CDC, the US military healthcare professionals have all been interested in helping and sending aid to West Africa and trying to understand what was going to happen with the Ebola outbreak and plan a strategic operation to try and eradicate or at least control Ebola outbreaks in West Africa and other parts of Africa, potentially Central Africa. So you can see the date there is June 11, 2013, when this model was kind of released to the public. This model is called Cellsome, and this model is the model that we built for the California Department of Fish and Wildlife. And it's got quite a pretty front end, and I didn't have much to do with programming the front end because I don't really know how to do this, but I had all these wonderful students who can do this stuff. And so we built this nice front end, and we can run the model, we can do baseline studies, we can start the brood year at a particular point in time, we can run for a number of years. I was working with people who model the hydrology of the system, and they were responsible for the river flow simulations that go on behind this. And so you can run the simulation. So you go here and you press run simulation, and the simulation runs for a couple of minutes, and then you get some output. And so we have this nice graphic front end with the river system that shows the salmon coming up. Now, every simulation will be unique in terms of the graphics that will come up. So I made a little movie here. I can actually bring this online later if anybody wants to see, and we can run it. So let's run the movie. And the movie's going to take a long time to run, so I'm going to drag this along, and you'll just see different phases and things happening. You can see as we run through on a weekly time interval, the basic iteration here. And then as we go through different phases, different kinds of information comes up. This is a year, a summary. You can see the age structure of the fish coming up. You can see then the age structure of the smolts coming down. You can click on individual years, and then you can choose the different river systems, and you can see information on flows, and you can look at the number of different life stages at different weeks in time, and so you can play around with this model. So it seems like a wonderful model, and people should use it, but should they really use it? That's the question. I mean, after spending, I don't know, shouldn't say this too loud. I mean, $1 million, I'm sure, on this. Why did we build it, and what do they want to do with it? They actually wanted this model, and they wanted to have a model like this out there for people to use. And there are different stakeholders, and different stakeholders can use this model. Would I put my head on a block for any particular piece of information that comes out of the model? I wouldn't. But I know this. Who else knows it? I mean, this looks great, so how much credibility does it have? Okay, so that's the first one. Here's the second one, is talking about the Ebola crisis. And everybody's very familiar with this. Tremendous outbreak compared to all previous outbreaks on the 30, 40 years before that, and a large crisis with lots of coverage. And this time, there was a lot of fear that Ebola would spread via people flying from West Africa to different countries, and people calling for airports to be shut down and all this sort of stuff. And then the Center for Disease Control had websites and a lot of information online. And then the CDC released their estimate of the future number of estimating the future number of cases in Ebola epidemic, Liberia and Sierra Leone. And for some reason, they did the most appalling job at estimating that you could possibly do, which is if a line goes up geometrically, you just continue it geometrically forever. And so we had this incredible panic which said without additional interventions or changes in community behavior, CDC estimates that by January 2015, there'll be approximately 500,000 Ebola cases in Liberia and Sierra Leone, or 1.4 million if corrections for underreporting are taken into account. Huge panic. Be pardon? Yeah, ridiculous numbers. Where did they get them? They, as I said, you know, like there's so many cases per week, 2%, blah, blah, blah. Let's go. So to contrast that, this is the actual number of cases by 13th of September 2015 was 28,000 compared to 1.4 million. And people were going to make decisions, you know, certainly politicians were like, okay, let's close all the borders, let's take medical personnel coming back and incarcerate them in Fort Knox or whatever and never let them out. People were going crazy. So we decided, we had actually started building a model before this, and by the time that prediction came out, our model that we were running showed that this was just a crazy number. And in our paper, we actually looked at some of the data. And the thing about some of these models is that some of the early models coming out on Ebola were just saying, okay, we've got a homogeneous population of so many people, and if you simulate an outbreak in a population like that, depending on the R0 value, which is the reproductive value, this is going to climb at a particular rate, but you're going to get something that looks like this. If you looked at actual chiefdoms in different areas or districts, you would see this kind of pattern, which looks nothing like this pattern. So you know that the assumptions of those models are just hopeless and that the models don't work like that. We built a transmission chain model, which is an individual-based model, and I don't want to go through much to this, but this is just a kind of a stochastic process with details that we were interested in. And we built this model, and we made some assumptions about the rate at which risk will be reduced over time, and this should be taken into account, which is essentially why the outbreak did not follow the kind of pathway that people had been estimated early on. We looked at the probability of isolation. And then we built our model using our new NOVA platform, which allows us to use graphical elements to build a JavaScript that we can then run anywhere. In fact, we can run the script on high-performance systems as well. And so we can run it very rapidly. We can run it in a web browser. We can run it in different places. And the idea in building models like this is that It has different elements, and we know exactly where little pieces of code are, and we can go in and change those pieces of code if we want to modify things. We've got aggregators for controlling all the agents, so we don't have to program these things up. We've got a lot of tools, so that in the end we can very rapidly build a JavaScript program that we have a lot of confidence in the accuracy of the coding if we've done the right thing in the way we've put it together. And then we built, from this, we have a way of turning these JavaScript programs into these apps. Now here, we built this app as a demonstration of what we can do. This is for a homogeneous and not for a heterogeneous population, so there's no spatial structure. We can bring in spatial structure into this, but there's no spatial structure in this. And this is available online. We actually haven't made it freely available because we don't want people to necessarily just use it. And again, for the reasons, so here I can show how you can graphically change certain of the elements, then you can run the model, and you can get predictions. Now, this is a model which we've created. If we just made it freely available, and somebody in CDC or the United States Army Health Division uses it to do stuff, they can plan on the basis of this model. And maybe they don't have a better tool out there for doing their planning. Maybe they'll just take this and do their planning. Should they actually be allowed to have access to this model for planning purposes if they don't really know what's in the model? So that's the real nub of the conundrum that we have here. So more and more complex system models implemented as web apps are becoming available for general use. So the question is, are we thereby enabling Hawkins' aphorism, which is the greatest enemy of knowledge is not ignorance, it's the illusion of knowledge. So we're providing things out there, people take them, and then they're under the illusion that they can have some knowledge about what's going to happen, and they can use that to manage and do important things, spend lots of money. If that is true, can we mitigate this through education? So do we need to insist that anyone using someone else's model should at least have some experience in building their own models of similar, albeit simpler systems? So if somebody at the CDC wants to use my model, should they contact me to talk about it? Or should I have sufficient documentation that if they're well educated and they read through it, they understand what all the basic assumptions behind this model are, what the strengths and what the limitations may be? So my feeling is that model building experience is critical when it comes to using what I call the canned models of others. And maybe we should have some process where we require individuals to have model user licenses. In other words, somehow it becomes recognized that people who are going to use models and do not only do modeling, but take advantage of modeling technology and the models built by others out there, are at least at the level where it's equivalent to what we think of as a master's level degree in the health sciences. So somebody gets a position in the county health offices or the state health offices. They can't be appointed unless they have appropriate qualifications. Should we be able to appoint people who have the power then to use other people's models for purposes of management and making decisions if they aren't appropriately qualified? And how can we begin the process of ensuring that people do get the appropriate qualifications and this becomes nationally recognized? And so, as I say, the healthcare system is one model. You can't be a doctor's assistant or what, I'm not sure what the term is, a physician's assistant, unless you have considerable healthcare qualifications yourself. You can't be a nurse unless you have a nursing degree. All these sorts of things. So we need to maybe develop a culture out there where people realize that powerful computational models are going to become available, and we shouldn't be rebuilding the wheel, and we shouldn't be rebuilding the rockets and the vehicles that allow us to explore this complex system space. But at the same time, it shouldn't be a free-for-all and anybody can just get into a particular rocket and drive it around. You've got to get a license to operate a heavy-duty truck or whatever if you're going to drive a heavy-duty truck. So that's pretty much my thoughts that I thought I would throw out there, and maybe we'd have more chance to discuss these ideas. Thanks. Oh, okay.
So Steve Gould once said, nothing is more harmful to science than false facts. And it's very similar to the Hawking thing about things. So let's go back here. Leslie will go first.
So it seems one potential solution for not having unqualified people implement a model is to not make a slick front end that it's very easy to put data or parameters in the model and get something out. Like if all you publish is the mathematical model that underlies it, the only people who are going to be able to use it are people who are more sophisticated. Not that they won't make the same mistakes, but it at least separates you from that danger a little bit, I would think.
Okay. I mean, that is true, and we have this perennial problem of we do stuff, we have to get money to do it. It's like the astronautics community and wants to go to Mars, but we've got to send humans there because that's the only way we'll get money instead of just sending machines. So it's the same sort of thing. This was kind of driven by the people at California Department of Food and Wildlife. They wanted a nice front end to show what is going on with the model when you run it. And as you can imagine, the students said, wonderful, we want to build that for you. And in order to keep the whole process going and make it attractive to the public out there, they want to see the great front end. But we don't want them to use it because of that. So you're right, there is this so do we lock it behind some kind of door? When somebody who knows how to use this actually uses it and then talks to a community about it, then it's good to have this nice front end to illustrate your ideas. Because then it's just not a bunch of graphs, but you can see the fish going up the river and you see the little graphs of different amounts. So it's true. There's a trap there that we can fall into. And we fell into it.
Okay. Fred's next.
So especially this last part I thought was very intriguing, the idea that maybe you have to develop standards or licensing processes or sequences of tests like you might have for the folks who want to go into insurance. And is that really feasible? I mean, can we really say somebody is a licensed modeler?
Right. So that is true. I mean, I was thinking about it in the healthcare industry. There are a lot of people out there who we call quacks, who we go to, who don't have a particular medical license, but who, I don't know, manipulate our bodies and claim that they can get rid of this problem or that problem, or we can go to herbalists and we can get stuff and they're not licensed. This is all true, and you can't stop that. But what you can do is you can develop a culture, certainly among government agencies, NGOs, people who hire, who want to look for the best, to say, okay, what are the standards here? What should we be looking for when we advertise? What should we list as a set of qualifications for this job? And a set of qualifications for this job could be a master's level degree in some applied computational sciences program. And if we don't start talking about it and we don't start the process of injecting that into the general discussion of how we use these models, nobody will. So we need to do that. And yes, I believe that ultimately governments who hire people will come to the point where they say, gee, what do you need for this job? You need a master's in an applied computational sciences field or something.
So it's not just government, but industry too.
Yeah, industry, whatever. So it becomes a standard that people recognize as what is the gold standard here. And it's like, when we go to see the doctor, we can go to somebody who's a licensed physician, or we know we're going to the local herbalist and what that may mean to us. We may have faith in it, that's our business. But at least the local herbalist is not going to be hired by the military to dispense drugs in Afghanistan or something.
Okay,
Carlos.
just before I give this to Carlos, there is an entire field of what's called dual use. There's many NRC, National Research Council reports on issues of something that could be really positive with regard to a biological agent and something that could be really horrifying. So there are international agreements about effective management of something that could lead to bioterrorist or other attacks. It might be useful to look at that literature and learn from it.
I think that the biggest challenge that we have in science is how to address uncertainty, and that comes just absolutely everywhere. And but I think that whether people know modeling or they're good or not, I think that there is also the general idea who gets more visibility, who makes the biggest predictions. I mean, those numbers by CDC, everybody knew that they were ridiculous, and nobody got up and spoke up, and so those are ridiculous numbers. In fact, the same thing happened in the past with the HIV epidemic. All the numbers were absolutely wrong, and nobody did.
Yeah.
Now, to our credit, we have done very well on those numbers. In the SARS epidemic, we predicted less than 400 cases in Canada, and there were 396 while the epidemic was going. And in SARS, we predicted 6,800 cases by the end of September, and there were actually 7,000. But I think that the key thing is that long-term predictions is really difficult. And I think that focusing just on predictive models, prediction is sort of what people like to hear, but short-term prediction is probably the best that we can do in most instances. And I think some recognitions about the limitations in modeling, just like people do when they do ecological studies. I remember Peter Carib at one point showed a distribution of the studies of the ecological sites, and he showed that most of them were 10 square meters, hardly any replications, and very few have very, very long size. From those studies, we cannot really make great predictions about what's going to happen at large scale in ecology, but that's the best that we have. There is a lot of uncertainty. We get some understanding. But providing a lack of clarity on those is by all scientists as well as by other people, that's part of the problem, because we're always worried about funding, we're worried about whether they're going to support these activities or not. So I think that we are also partially responsible for that, and I think that's one of the big problems. What we could predict in the case of Ebola very, very clearly is that the extraordinary pandemic of Ebola in the United States that involved 5 cases, 4 exported cases, was the pattern of Ebola was perfectly predicted by the television news. So we published a paper where exactly we matched perfectly to the data the news coverage with the numbers of requests and Google and other things associated with the fear of Ebola, where all sorts of really stupid questions were being asked about the possibility that somebody might get Ebola. I just sent you the paper.
Let's thank Wayne again.